Hello, everybody. I'm going to present you the work titled Deep Learning as a Tool to Recognize Diffraction Patterns on the Far Field. This project was carried out by Dr. Pedro Arguijo from Tecnológico Institute of Misantla and me, Dr. Lizbeth Castañeda of Tecnológico Institute of Xalapa, both from Mexico. Diffraction. The term diffraction has been defined by Sommerfeld as any deviation of light rays from rectilinear paths, which cannot be interpreted as reflection or refraction. Goodman mentioned that diffraction is caused by the confinement of the lateral extents of a wave, and is most distinguished when that confinement has a comparable size with a wavelength of the radiation being used. When both the distance from the light source to the aperture and the distance from the aperture to the observation plane are infinity, we talk about the Fraunhofer diffraction. We can find various diffraction patterns with different forms of apertures. This has led to the use of this process in other areas and with other goals. Seeing and recognizing an object whose size is much smaller than the illumination with light is a challenging task for an observer placed in a far field. Fraunhofer diffraction field do the diffraction limit. On the other hand, the importance of using the Fourier transform for recognition of images through their diffraction pattern is known. We know that diffraction images record angle resolved distribution over scattering light for an object and coherent light and can correlate highly with the morphology of the object. This diffraction pattern recognition technique has been used, obtaining the fast Fourier transform, FFT, to identify the morphology of codepod, which are a subclass of small maxillop crustaceans widely spread throughout the planet. On the other hand, Rigosi studied the limits of various national have also been used as aperture to obtain the FFT and observed the diffraction patterns related to the coastlines of country system. In this work, we obtained through FFT the far field diffraction patterns of non-symmetrical apertures. The considered apertures are the MNITS dataset. In the year 2001, emerged a new machine learning branch, which had gained much attention due to their ability and flexibility for learning complex patterns. Machine learning's popularity and the development of more advanced computational capabilities allowed the arrival of this innovative technology. This new area encompasses several techniques characterized by hierarchical learning process, in which starting from low-level structures, higher-level structures are built through multiple layers. This deep learning has been successfully applied to various problems, such as image classification, digit recognition, and speech recognition, among others. In machine learning, character engineering is performed to represent the input object. Once extracted comes the process of training the classifier. And in deep learning, the engineering of characteristic is not performance because the architecture performs the extraction and classification. We consider has diffraction apertures, the MNITS Este dataset, which is arguably the best studied and most understood in the literature of machine vision and machine learning algorithms, used on the handwritten digit classification problem. The dataset consists of 60,000 training examples and 10,000 test examples of handwritten digits from 0 to 9, written by different people to avoid correlations. Each digit is represented as a 28 per 28 pixels grayscale image with black background and a white character centers in the square. In this figure, you can see 10 different handwriting digits, and as can be seen, there exist ambiguities on different classes. For example, there are some 7s that look like a number 1. For our experiment, we resize each image to 62 and 62 pixels with a padding of zeros, leaving the character center. The total number of instances in the training and test sets are distributed equally among 10 classes, as shown in the table. We show the corresponding Fraunhofer diffraction patterns of 5 random digits of each character. Although the character cannot be considered as symmetrical apertures, the diffraction pattern shows symmetry. You can see this in this picture, the number 4, 5, 6, 7, and 9. In this part, I will explain in more detail how the deep learning works. Deep learning can understand high-level abstractions through computational structures that allow addressing multiple nonlinear transformations. Deep learning systems share several characteristics. There is its ability to process multiple layers in a non-linear way. On the other hand, supervised or unsupervised learning of this layer is carried out to reach increasingly complex abstractions. Each layer occupies a place in the hierarchical scale of the neural network and represents a higher level of complexity and abstraction. Convolutional neural networks, CNNs, are a set of deep learning algorithms that have the particularity that convolution and pooling operations are performed between their hidden layers. This operation acts as extractor of the most important features within the network architecture in the learning process. It should be noted that this process is similar to feature engineering and is done implicitly within the network architecture. A CNN architecture basically contains an input layer, multiply hidden layers, as well as the output layer. The hidden layer basically consists of convolutional layers, pooling layers, and fully connected layers. In these figures, you can see the deep learning architecture. Convolutional layers are understood as a set of filters, commonly called receptive fields. Its main purpose is to extract features from an image and reduce the complexity of the system. Such set of filters are trainable, and their values are learned for activation upon encountering certain features. These learned features pass through a next layer of filters to reach the output layer. The feature map is a two-dimensional matrix that highlights the areas of the image that are more consistent with the kernel values. An example representing this operation is shown in this figure. The total feature maps generated at the output layer is equal to the number of layer filters. In this way, we can see the output as a new image whose number of channels is equal to the number of layer filters. The extracted features correspond to each possible location of the filter in the original image. This process has the advantage that the same filter can extract the same features anywhere in the input, reduce the number of connections and parameters to train. Convolutional layers have specific parameters called hyperparameters that determine the output of this layer: filter size, number of filters, padding, and straight layer. This layer allows the reduction of the spatial size of the input image, which leads to reduce the number of parameters, the computational load, and the memory used to control the risk of overfitting. In addition, with this reduction, the neural network can learn and tolerate small changes in the image. Like the convolution layers, this pooling layer is connected only to some input neurons. In addition, its size, stride, and the type of padding to implement must also be defined. However, a characteristic of this layer is that it does not have weights, since it only performs a subsampling operation. The most popular used pooling layers are max pooling and average pooling. The way in which the pooling layer operates is shown in this figure. Fully connected layers. In this layer, each node is fully connected to the output of the previous layers. Each node does a weighted sum of its parameters by the input value and the independent input or bias. With this, the one with the highest score will be the one with the highest probability. In fact, they make a classification indicating the probability of each class. For the problem of classifying diffraction patterns images, we adapted a CNN model that resembled the BGG architecture with a receptive field of 62 per 62 per 1 pixels. As any CNN architecture to classify images, it consists of two parts: feature extraction and feature classification. The architecture of the proposed CNN used in this work is detailed in this table. It consists of 5 convolution layers, 3 max pooling layers, and 2 fully connected layers. Stride for convolution and max pooling was set at 1 in both cases. The feature extraction comprised convolutions of kernel 3 per 3 with features maps of 32, 64, and 128 max pollution layer of size 2 per 2. The classification layer contains a flattened layer, a dropout layer of size 0.2, 2 dense layers of size 512 and 10 respectively. A ReLU between the 2 dense layers and the sigmoid activation functions thus performs the classification task. Training was performed using Adam optimization with batches of 64 images for 10 epochs. Of the total instance on the training set, 12,000 random diffraction patterns were used for validation, and the remaining 48,000 diffraction patterns for training. We evaluate the performance of the proposed CNN with several standard measures, such classification, accuracy, precision, recall, which are derived from the confusion matrix. The measures ACC, P, and R are defined in terms of the numbers of true positives, true negatives, false negatives, and false positives. Accuracy measures the ratio of correct predictions over the total number of instances evaluated. Precision measure the positive patterns that are correctly predictive from the total predicted patterns in a positive class. Recall is used to measure the fraction of positive patterns that are correctly classified. These metrics are defined as this equation. This is the confusion matrix. The confusion matrix that depicts the result of classification of the diffraction patterns. The diagonal elements are the number of instances where the predictive label was the same as the actual label, while the off-diagonal values indicate the challenges encountered by the system in classified individual classes. It is clear from the confusion matrix that the CNS has performed excellently on classes 1, 0, and 4. Also that the toughest classes for classifications are 6, and 9. The precision and recall of each class are displayed in the table. As shown in the table, except for recall of classes 6 and 9, the results are higher, about of 94% for each metric. The overall classification accuracy obtained was of 0.9611%. The conclusion. We have proposed a CNN architecture to classify diffraction patterns, obtained of the well-known benchmark for handwriting digit recognition, the MNIST dataset. All results suggest that using deep learning techniques to analyze real diffraction patterns that arise in different areas is possible. This is the reference, and thank you very much for your attention.